The last Starship is no longer carrying passengers toward a distant world. It is carrying every human life that remains. Behind it, Earth has gone silent, and ahead, there may be no planet waiting to receive them. The ship must now become more than a machine. It must provide air, water, food, medicine, shelter, knowledge, and enough stability for children to grow up inside a world built from metal. Yet every system has a limit. Every spare part eventually runs out. And even a perfect machine would still depend on people who can survive isolation, conflict, illness, and the slow loss of everything they once called home. So tonight, the question is simple. How long could the last Starship keep humanity alive? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. If you could save only one part of human civilization aboard the last Starship, what would you choose? Let me know in the comments. I will pin the most thoughtful answer. Tonight, you are watching the Just About Space channel, talking about how long could the last Starship keep humanity alive. At the beginning, nothing inside the ship would seem different. The lights would still follow their programmed rhythm. Air would continue moving through hidden ducts. Pumps would carry water between tanks, filters, and living quarters. Somewhere in the agricultural decks, rows of plants would open toward artificial morning, while the navigation system quietly corrected the ship's course against stars too distant to change by any visible amount. The crew might wake, eat, work, and speak to one another exactly as they had the day before. Only one thing would be missing: the signal from Earth. A lost transmission would not immediately mean the end of the world. Deep space communication is never as simple as a conversation across a room. Messages can be delayed, weakened, distorted, or blocked by equipment failure. A ground station could lose power. A relay might turn away at the wrong moment. Solar activity could interfere with the signal, and a damaged antenna on the ship could create the illusion that Earth had vanished when the failure was actually much closer. For hours, perhaps even days, the crew would treat the silence as a technical problem. Engineers would test receivers, change frequencies, reposition antennas, and compare every clock against the expected arrival times of scheduled transmissions. The silence would become disturbing only because it continued. Every long-distance mission would carry procedures for communication loss. The crew would know what to check, what to restart, and how long to wait before moving from one possibility to another. They would search for automated beacons, emergency channels, scientific transmitters, old satellites, and any signal strong enough to suggest that something was still operating near Earth. The ship might turn its largest antenna toward the point where the planet should be, even though by then, Earth would appear as little more than a calculated location, hidden in the light of its star. At first, the crew would probably avoid the most frightening explanation. Human beings are good at living inside uncertainty when there is still a practical task to perform. As long as another diagnostic can be run, another channel can be opened, or another software fault can be examined, the silence remains a problem with a possible solution. It is only when the list of ordinary failures becomes exhausted that the meaning of the silence begins to change. Perhaps one message arrives, but it is incomplete. A fragment of data, a corrupted warning, or a final transmission sent years earlier might reach the ship after the event itself has already become history. In deep space, there is no true present shared between a spacecraft and the world it left behind. If the ship is several light years away, every image from Earth is already old when it arrives. The crew would not be watching events unfold. They would be receiving a delayed record of a planet that may no longer exist in the same form. That delay would make certainty almost impossible. If Earth stopped transmitting, the ship would not know whether humanity had disappeared. whether civilization had collapsed, or whether a smaller disaster had destroyed only the systems capable of reaching them. The planet might still be alive and full of people, yet unable to send a signal across interstellar distance. Governments could have fallen while cities remained. A new society could have emerged with no interest in maintaining the old communication network. Earth may have survived, but changed so completely that the ship no longer belonged to its future. For the people on board, those possibilities would offer little comfort. They could not simply turn around to investigate. A starship far beyond the solar system would be moving along a path that required enormous energy to alter. Even if a return were technically possible, it might take decades or centuries. The crew would have to decide how much fuel, time, and risk they were willing to spend chasing an answer that could no longer help them. By the time they reached the place where Earth had been, every person who remembered the departure might be dead. The ship would continue forward, because motion in space does not wait for certainty. Its engines might be inactive, yet momentum would carry it onward. Navigation corrections would still be required. Crops would still need tending. Children would still need care. Machines would still fail at ordinary times, without respect for the possibility that an entire civilization had gone silent behind them. The crew could grieve, argue, or refuse to believe what had happened, but the ship's systems would continue demanding attention. This is where the mission would quietly change its purpose. Before the silence, the Starship would have belonged to a larger human world. It may have been one vessel among many, supported by laboratories, industries, observatories, governments, and families spread across Earth. Decisions made on board could be checked by thousands of specialists. Software updates could arrive from teams who understood systems more deeply than anyone on the ship. Medical advice could be requested, navigation plans revised, and new information about the destination transmitted while the vessel was still in flight. Even if no physical supplies could reach the ship, the mission would still be connected to a civilization far larger than itself. Once that connection disappeared, the crew would inherit everything. They would become the final authority on medicine, engineering, law, education, agriculture, and survival. There would be no distant expert to consult when a problem exceeded the knowledge of the people awake at that moment. No replacement mission could be launched. No rescue vessel could follow. The ship's databases might contain vast libraries, but information alone does not repair a machine, diagnose a rare illness, or hold a frightened community together. Knowledge must be understood, practiced, and passed from one person to another, and every generation would have fewer living memories of the world that created it. The oldest passengers would carry memories that no one born on the ship could share. They would remember open air without filtration, real sunlight, weather moving across the sky, and distances measured in roads rather than years of travel. Those memories would suddenly become more than personal stories. If Earth were truly gone, they would be among the last direct witnesses to the planet as a living human world. Their children might understand Earth through recordings and lessons. They could watch oceans rise and fall against beaches, see animals moving through landscapes, and hear languages that no one on board still spoke fluently. Yet there would always be a difference between knowledge and memory. To a child born between stars, Earth could feel both completely real and impossibly distant, like a place from history that had once produced every object, custom, and human body around them. The crew would have to decide what to tell those children. They could not honestly promise a return home. They might not even be able to promise that a habitable destination existed ahead. The Starship could be traveling toward a planet selected from observations made long before launch, when its atmosphere and surface were still uncertain. A world that looked promising across interstellar distance could prove hostile when the ship finally arrived. The journey might not end with landing. It might end with another decision to continue. In that situation, the word home would begin to change. For those who remembered Earth, home would remain behind them, silent and unreachable. For those born during the journey, home would be the ship itself, its corridors, sleeping quarters, gardens, machinery, and carefully maintained routines. The same metal walls that felt confining to one generation might feel protective to the next. A window showing darkness could be a reminder of loss to an older passenger and an ordinary view to a child who had never seen anything else. This change would matter because survival depends partly on what people believe they are preserving. A temporary crew can endure hardship for the promise of arrival. A rescue mission can accept strict rules because it expects to return. But the last Starship might need people to maintain a society with no clear ending, no outside authority, and no guarantee that the destination would be better than the vessel carrying them. The mission could no longer rely on the idea that everyone was simply passing through. The crew would need a new explanation for why the work mattered. Each repaired pump, planted seed, and medical lesson would become part of a chain extending beyond the lives of the people performing it. An engineer might maintain a water system not for personal survival alone, but for children not yet born. A teacher might preserve a language no one needed for navigation because it carried a way of thinking that would otherwise disappear. Someone would have to record mistakes honestly, even when those mistakes involved respected leaders, because future generations could not afford to repeat failures hidden for the sake of comfort. These questions would emerge slowly through ordinary events. A child would ask whether Earth still existed. A technician would request parts that could not be replaced. A group of passengers might demand another attempt to turn homeward. A funeral would be held for someone whose body could not be returned to the planet they remembered. Each moment would make the new reality harder to deny. Yet even then, no one could be completely certain that Earth was gone. A signal might still arrive after years of silence. It could be weak, delayed, or sent by a civilization that had survived in a form the crew barely recognized. The possibility would remain because deep space preserves distance not only in kilometers, but in time. Earth could be alive while the crew mourned it. It could have died while they still believed rescue was possible. The ship would have to build its future without ever receiving the certainty that people usually seek before changing their lives. There would be no clear moment when the old mission ended and the new civilization began. No announcement could make the transformation complete. The ship would simply continue operating while its connection to the past grew weaker, until one day the people on board realized that they were no longer supported by humanity. They were humanity. From that moment, every system inside the vessel would take on a different meaning. Air would no longer be a service provided to passengers. Water would no longer be cargo. Food would no longer be a supply calculated for the expected duration of a journey. These would become the basic conditions of an entire world, and the ship would have to provide them without the planet that once made life seem almost effortless. The greatest danger would not necessarily begin with a broken engine or a collision in the dark. It could begin with a small imbalance inside a system everyone assumed would keep working. A filter that removed slightly less contamination each year. A crop that produced fewer seeds. A chemical that could not be fully recovered. Or a piece of equipment that required a material no longer available. On Earth, such losses are hidden inside a vast environment and a global economy. On the last Starship, nothing truly disappears. Every missing gram, every damaged component, and every failed cycle remains part of the ship's future. The silence from Earth would therefore reveal something the mission may not have been designed to face. A starship can be built to travel for a long time, while still depending on a world beyond itself. It can carry spare parts without being able to manufacture every replacement. It can recycle water without recovering every trace. It can grow food while relying on nutrients stored at launch. It can protect a crew without being capable of supporting a civilization indefinitely. The difference between a long voyage and a permanent human world is much greater than distance alone. To keep humanity alive, the The ship would need to close every loop that Earth once closed naturally. It would need to turn waste back into useful material, carbon dioxide into oxygen, and human labor into a stable system that could survive mistakes. It would have to do this not for a mission measured in years, but for an uncertain future in which no outside source could restore what had been lost. And so, once Earth went silent, the central question would not be where the Starship was going, but whether its metal walls could contain everything a living world requires. A planet hides most of its support systems from the people living on it. Air moves because an atmosphere surrounds the world. Water falls, flows, evaporates, and returns through cycles so large that no single person needs to understand every part of them. Soil stores minerals, carbon, microorganisms, and the remains of earlier life. Heat arrives from a star, while gravity holds oceans and gases close to the surface. Earth can be damaged or pushed out of balance, but it still offers an immense natural buffer between human life and immediate failure. A starship would have no such buffer. Its atmosphere would be a measured quantity sealed inside a pressure hull. Its water would exist only in tanks, pipes, bodies, crops, and storage. Every useful material would have entered the vessel before launch or been manufactured from something already on board. Nothing could be treated as truly disposable, because anything thrown away would still remain somewhere inside the same closed world. The ship might feel large to the people living within it. Its corridors could extend for kilometers, with schools, clinics, workshops, gardens, and quiet spaces designed to resemble parks. Artificial windows might display changing skies, and rotating sections could create enough gravity for ordinary movement. Yet compared with Earth, even an enormous vessel would be a nearly empty shell carrying a small inventory of life. That difference would shape every decision. On Earth, a person can open a window without calculating the total amount of oxygen available to the population. On the ship, every breath would be part of a managed cycle. Oxygen consumed by people would return as carbon dioxide, water vapor, heat, and waste. Machines and plants would have to separate, transform, and redistribute those products before they became dangerous. The process might work so smoothly that passengers rarely noticed it, but the apparent simplicity would depend on thousands of systems operating together. Air would be among the clearest examples. Human beings do not require pure oxygen, but they do require a stable mixture of gases at a safe pressure. Too little oxygen would weaken the body and cloud the mind. Too much could increase fire risk. Carbon dioxide would have to remain low enough for people to think and sleep normally, while traces of chemicals released by plastics, machinery, cleaning products, and human activity would need to be removed before they accumulated. A filter does not simply make bad air disappear. It captures or transforms particular substances, and eventually its useful material becomes saturated or degraded. Some systems could be regenerated with heat or chemical treatment. Others would depend on replaceable components. The ship would need several overlapping methods, so that one failure did not threaten everyone at once, but every backup would add mass, complexity, maintenance, and another set of parts that could eventually fail. Plants could support the atmosphere by taking in carbon dioxide and releasing oxygen, yet they would not turn the ship into a self-balancing forest. Crops also breathe. Their behavior changes with light, temperature, disease, and stage of growth. Roots, stored food, decomposing waste, and the organisms living around them would all exchange gases with the environment. Biology could support the machines, but it would introduce living variables that could never be controlled as precisely as a valve. This is why a true artificial world would need layers of control, rather than one perfect loop. Mechanical equipment could remove carbon dioxide quickly during an emergency. Plants could provide long-term support while producing food. Chemical reserves could stabilize the atmosphere, if part of the biological system failed. Sensors would watch pressure, humidity, temperature, oxygen, carbon dioxide, and substances that people might not detect until they had already begun causing harm. Those sensors would become part of the ship's perception. A planet does not need to know how much atmosphere it contains in order to keep it. A starship must measure itself constantly. It would need to notice a slow leak behind a wall, an unusual chemical signature in a living area, or a small rise in carbon dioxide that suggested a failing circulation fan. The crew would live inside a world that survived by examining every part of its own body. Water would appear more familiar, but its cycle would be equally unforgiving. People would drink it, cook with it, wash in it, and release it through breath, sweat, urine, and waste. Plants would draw it through their roots and return much of it to the air. Cooling systems, laboratories, and workshops would require it in different levels of purity. The same molecules might pass through a person, a filter, a crop, and a storage tank many times within a single year. Much of that water could be recovered. Vapor could be condensed from the air. Wastewater could be filtered, distilled, treated through membranes, and cleaned of microbes and chemicals. The result might be safer than water found in many natural environments. Yet recovery would never be effortless. Pumps wear down, membranes become blocked, seals leak, and some contaminants are difficult to separate. A small loss repeated over decades becomes a serious reduction in the ship's total supply. This creates a difficult balance between efficiency and resilience. A highly optimized system may waste almost nothing under ideal conditions, yet become fragile when one component fails. A simpler design may be easier to repair, but lose more water or energy with each cycle. The last Starship could not rely entirely on either approach. It would need systems efficient enough to preserve scarce resources, and simple enough for future generations to understand and rebuild. Waste would no longer be a category of unwanted material. It would be a temporary condition. Human waste contains water, carbon, nitrogen, phosphorus, salts, and other elements that living systems need. Food scraps contain chemical energy and nutrients. Damaged clothing contains fibers that might be recovered. Broken equipment contains metals, ceramics, plastics, and electronic materials that could become useful again. Turning all of this back into safe resources would be one of the ship's most important industries. Biological treatment could break down organic waste. Heat and chemical processing could separate useful compounds. Mechanical systems could sort and grind damaged objects. Some materials might be melted and formed again, while others would degrade each time they were recycled. A plastic component could not always become the same component again, and mixed materials would make recovery more difficult. Earth spreads these processes across enormous geological and biological systems. A fallen tree becomes food for insects, fungi, and microorganisms. Minerals move through soil and water. Waste can be decomposed, absorbed, or buried over long periods. The Starship would have to compress those same functions into rooms that could be cleaned, monitored, and repaired by people. Heat would also have to be managed. Every person, computer, lamp, motor, and growing plant produces it. On Earth, excess warmth can move into the atmosphere, oceans, or ground. In space, the ship could lose heat only by radiating it away from its outer surface. Large radiators would carry thermal energy from the interior and release it into darkness, while insulation protected other areas from becoming too cold. The balance would shift as systems changed. Agricultural lighting might operate more intensely during certain growing cycles. Workshops could produce bursts of heat. Population growth would increase the warmth generated in living areas. A damaged radiator could force the crew to reduce energy use, close sections of the ship, or allow temperatures to rise. The artificial world could develop its own kind of weather, created not by clouds and oceans, but by ventilation patterns, moisture, machinery, and the uneven movement of heat through metal. Energy would stand behind all of these cycles. Air cannot be circulated, water cannot be purified, waste cannot be processed, and crops cannot grow under artificial light without dependable power. A ship traveling between stars would receive little useful energy from sunlight unless it passed close to another star. Its main supply might depend on nuclear reactions, stored fuel, or some technology built to operate for extremely long periods. Even a powerful reactor would not make energy unlimited. Components exposed to heat, radiation, and stress would age. Fuel would be consumed. Every system drawing power would compete with another need. Life support, navigation, manufacturing, medicine, computing, and protection. During ordinary years, the ship might provide comfortable lighting and generous living space. During a long emergency, comfort could become a resource that had to be reduced. The crew might dim public areas, lower temperatures, shorten agricultural light cycles, or close unused sections to conserve power. These choices could protect essential systems, but they would also change the emotional character of life on board. A vessel designed to feel open and humane could gradually become darker and more confined as its energy margins narrowed. People would experience decline, not as one dramatic failure, but as a slow loss of options. Over generations, the layout itself might change. A storage deck could become living space as the population grew. An empty module might become a workshop, clinic, or nursery. Materials would be moved, walls rebuilt, and systems rerouted according to needs the original designers could not predict. Adaptability would be essential, because no plan created on Earth could perfectly anticipate centuries of life in deep space. This changes the meaning of advanced technology. The most impressive machine is not always the one that performs best when new. On the last Starship, a valuable system would be one that could be inspected, explained, repaired, and eventually recreated by people born long after its designers had died. A sealed device that worked flawlessly for 50 years and then failed without warning might be less useful than a less efficient machine that could be rebuilt indefinitely. The crew would need records showing not only how systems were intended to work, but how they had actually changed. Every repair, leak, contamination event, and software modification would become part of the ship's medical history. Without accurate records, future engineers might treat an old workaround as original design, remove a component that had become essential, or repeat a failure whose cause was no longer remembered. The artificial world would depend on memory as much as machinery. A pipe carries water only while people know where it leads. A filter protects the atmosphere only while someone understands when it must be regenerated. A reactor provides power only while its warning signs can still be interpreted. Knowledge would have to move through generations with the same care as air and water move through the ship. Still, no amount of planning could make the vessel perfectly closed. Tiny leaks would release gas. Materials would become trapped in forms that were difficult to reuse. Radiation would slowly alter electronics and weaken structures. Human activity would create new chemical mixtures that had not existed at launch. The ship could reduce these losses, but it could not pretend they were not happening. Long-term survival would depend on keeping the rate of loss below the rate at which the community could adapt. A missing resource might be replaced with another material. A failing system could be redesigned. Sections of the vessel could be dismantled to support those that remained. The ship might slowly consume parts of itself, sacrificing unused structures so that essential ones could continue. Its apparent size could therefore be misleading. It might begin as a vast habitat, but not every room would remain available forever. Some spaces could be sealed after damage, stripped for parts, or abandoned when maintaining them required too much energy. The living world might gradually contract around its healthiest systems, becoming smaller as centuries passed. And yet, Contraction alone could not preserve humanity. Air, water, heat, and shelter keep bodies alive. But a closed world must also replace the energy and matter those bodies consume every day. The ship could recycle nearly everything, but its people would still need a continuous source of food. And that requirement would turn the vessel's quiet gardens into one of the most important and vulnerable systems aboard. Stored supplies could carry a crew through the opening years of a journey, perhaps even through decades if the ship had been launched with enough mass. Dried grains, preserved proteins, oils, medicines, and carefully packaged nutrients could be protected from moisture and contamination. Yet every container opened would reduce a reserve that could never be replaced from Earth. Even a vast warehouse would only delay the moment when survival depended on food grown inside the vessel itself. The gardens would therefore be more than pleasant rooms filled with green light. They would be farms, laboratories, air processing systems, and living stores of genetic material. Every plant would have been selected for a purpose. Some would grow quickly, others would provide dense calories, useful oils, protein, vitamins, or fibers. A few might exist because they tolerate disease, poor conditions, or changes in temperature better than more productive varieties. The ship could not afford to depend on crops that were impressive under ideal conditions, but fragile when the environment drifted. Space would shape the diet. Wheat, rice, potatoes, soybeans, beans, and other familiar crops might all be valuable, but none of them would be grown in the broad fields people remember from Earth. Their roots could sit in shallow trays, nutrient solutions, carefully structured soils, or chambers where moisture and minerals are delivered directly. Light would come from efficient lamps positioned close to the leaves. Temperature, humidity, and carbon dioxide would be adjusted with a precision no natural farm could maintain. That precision would create extraordinary productivity, but it would also hide a weakness. A field on Earth can survive a broken pump because rain may still fall and roots can reach moisture stored below the surface. A crop aboard the ship might depend on continuous circulation. If a valve remained closed for a few hours, an entire growing bed could begin to wilt. If the nutrient mixture changed, plants might appear healthy while slowly losing the minerals needed by the people who eat them. The garden could look alive and still be failing in ways that were not immediately visible. The crew would have to treat every harvest as part of a larger calculation. Calories matter, but calories alone do not sustain a population. Human bodies require proteins, fats, vitamins, salts, and trace elements in suitable amounts. A diet that keeps people from starving could still leave them weak, ill, or unable to raise healthy children. The agricultural system would need variety, even when variety used space and energy that could have supported a more efficient crop. Some foods would be easier to produce than others. Leafy plants grow quickly and can provide important nutrients, but they contain relatively little energy. Grains and tubers offer more calories, yet they require longer growing cycles and careful processing. Oils are essential, but oil-rich crops can be demanding. Protein could come from beans, microorganisms, insects, cultured cells, or animals small enough to fit within the closed ecology, though every option would carry its own costs. Food would also need to remain psychologically meaningful. People do not eat only to meet chemical requirements. Meals mark time, preserve identity, comfort children, and carry memories across generations. A community living inside metal walls might depend on shared food more deeply than expected. A recipe associated with Earth could become a ritual. The smell of bread, herbs, or fruit could offer a connection to a planet that no living person had seen. The gardens themselves could become important places of rest. Most of the vessel would be built from surfaces chosen for strength, cleanliness, and repair. Agricultural spaces would be different. Leaves would move in circulating air. Water would gather on roots and pipes. The smell of soil, even if the soil were artificial, would offer something no simulation could fully replace. Children might visit the growing decks as people once visited forests, learning that life can rise from darkness when given the right conditions. Yet the same living complexity that made the gardens comforting would make them hard to control. Plants do not grow alone. Their roots interact with bacteria and fungi. Nutrients move through microscopic communities. Some organisms help crops absorb minerals or resist disease, while others attack tissue, compete for resources, or produce toxins. A healthy agricultural ecosystem would require more than sterile surfaces. It would need carefully selected forms of life working together. Plant disease would be especially dangerous in a closed environment. On Earth, farms are separated by distance, climate, and geography. A disease that destroys one crop may leave others untouched elsewhere. A starship might carry only a limited number of growing zones, all connected by shared air, water, tools, and people. A fungus or virus entering one section could spread through the entire agricultural system before symptoms became obvious. Protection would depend on separation. Different varieties could be grown in isolated compartments. Seeds would be stored in shielded vaults. Tools and workers might pass through cleaning areas before entering sensitive rooms. Some crops would be kept dormant as backups, rather than planted continuously. The goal would not be to prevent every failure, which is impossible, but to make sure one failure could not erase the ship's ability to begin again. Seeds would become a form of insurance, though they would not remain viable forever. Temperature, moisture, radiation, and time slowly damage stored genetic material. Some species can remain dormant for many years, while others lose their ability to grow much sooner. The ship would need to renew its seed banks by planting old samples, collecting healthy new seeds, and returning them to storage. Nutrients would create another quiet limit. Plants need carbon, hydrogen, oxygen, nitrogen, phosphorus, potassium, and smaller amounts of many other elements. The ship might contain enough of these materials at launch, but they would not always remain in forms roots could use. Nutrients could become trapped in waste, deposited inside pipes, lost in damaged equipment, or mixed with contaminants. Recovering them would require constant work. Human waste could be processed and returned to the farms, but only after pathogens, medicines, and harmful chemicals were removed. Plant remains could be composted or broken down in controlled reactors. Food scraps would be too valuable to discard. Even wastewater from kitchens and living areas could carry minerals that the agricultural system needed. The closer the ship came to complete recycling, the more carefully it would need to control contamination. A cleaning chemical that seems harmless in a large environment could accumulate after passing repeatedly through water and crops. Medications released from human bodies might survive treatment and return in tiny amounts. Metals worn from machinery could enter nutrient solutions. Each trace might be safe alone, yet decades of circulation could create effects the original designers never tested. The agricultural decks would therefore reveal the true difficulty of a closed world. The challenge is not simply making material move in a circle. It is keeping that material useful and safe after thousands of cycles. Earth's ecosystems spread contaminants across oceans, soils, and long periods of time. The ship would compress those processes into a small volume where every mistake returns. Crop failure would not always arrive as a sudden disaster. It could begin with slightly smaller leaves, slower root growth, or a subtle decline in nutritional quality. Harvests might remain large enough to hide the problem until stored reserves had already been consumed. The crew would need to measure not only how much food was produced, but what that food contained and how the system was changing. A successful season could still leave the ship less secure if it used more fertilizer than the recycling system recovered, consumed rare replacement parts, or depended on a crop variety that was becoming genetically weak. Survival could not be judged by a single harvest. It would be measured by whether the farms could keep producing without quietly spending the future. Population size would be tied directly to this balance. Every additional person requires food every day, but agricultural capacity cannot always expand at the same rate. New growing space needs lamps, water lines, climate control, labor, and power. A ship designed for a fixed crew might struggle if the community grew beyond its original limits. Reducing the population would raise difficult questions, while increasing production would place more strain on the systems that supported it. So would the people who worked there. Farmers aboard the ship would be responsible for one of the most technically demanding systems in the vessel. They would need to understand biology, chemistry, engineering, disease control, genetics, and the emotional needs of the community. Their work could not be replaced by automation alone, because living systems create exceptions that no software can predict perfectly. Automation would still be essential. Sensors could monitor moisture, nutrient levels, leaf color, gas exchange, and growth. Robots might plant, harvest, clean, and inspect areas difficult for people to reach. Artificial intelligence could identify patterns across years of data, noticing a decline long before human eyes saw it. Yet these tools would be part of the same closed machine as everything else. Cameras fail, calibration drifts. Software becomes difficult to maintain. A farming system that no human could operate without automation would be powerful but dangerous. The crew would need the ability to continue at reduced capacity when advanced tools failed. Manual controls, simpler growing methods, and preserved practical knowledge would matter. The most productive farm might not be the most survivable one. Resilience would come from having several ways to produce food, even if some were slower or less efficient. Algae and microorganisms could provide that flexibility. They can grow quickly, use limited space, and produce protein, oils, vitamins, or oxygen. Bioreactors could turn waste gases and simple nutrients into edible material. Such food might not resemble traditional meals, but it could protect the population during crop failure. It could also support specialized systems that convert basic biological material into textures and flavors people find more familiar. Even with every method working together, food production would remain vulnerable to the ship's larger condition. A loss of power would darken the growing rooms. A failure in water treatment would reach the roots. Damage to the hull could force agricultural sections to close. A shortage of replacement electronics could reduce monitoring. The gardens would depend on machines, and the machines would depend on the people fed by the gardens. That circular dependence would define life aboard the last Starship. No system could be isolated from the others. A poor harvest weakens workers, reduces morale, and consumes emergency reserves. Tired workers make more mistakes. Delayed maintenance increases the chance of equipment failure. One damaged pump can become a nutritional problem months later, long after the original fault appeared to have been repaired. For a time, stored supplies and spare capacity could absorb these shocks. The ship might carry emergency food for years, dormant seeds, extra nutrient salts, and unused growing chambers. But reserves create safety only while they remain intact. Radiation, age, contamination, and repeated emergencies would slowly reduce them. Each crisis survived could leave the vessel less prepared for the one that followed. The gardens might continue producing for centuries, but only if the machinery around them could also be renewed. Lamps would dim, pumps would wear, pipes would collect deposits. Sensors would lose accuracy, seals would harden, motors would fail, and electronic controls would eventually need parts that no storage room could preserve forever. By then, keeping humanity fed would depend not only on the life growing under artificial light, but on whether the Starship could keep rebuilding the machines that allowed those gardens to exist. A vessel designed to cross interstellar space would begin its journey with layers of redundancy. Pumps would have twins. Critical computers would have backups isolated from one another. Spare seals, Bearings, circuit boards, valves, sensors, and cables would be stored in protected compartments, each one catalogued against the system it was meant to save. The crew might carry replacement units for failures expected during the first decades, along with raw materials for repairs no one could predict. For a long time, this could create the impression that the ship was prepared for almost anything. When a motor failed, another could take its place. When a sensor drifted out of calibration, a new one could be installed. A leaking pipe could be cut out and replaced. The work might be difficult, but the answer would still exist somewhere in storage, waiting inside a numbered container. The weakness of this approach would appear slowly. Every spare part is a decision made before launch. It assumes that engineers on Earth correctly guessed which components would fail, how often they would fail, and what kind of damage the ship would encounter. Some parts might sit untouched for a century, while another, expected to last the mission, begins breaking every few years. A storage room can hold thousands of replacements, but it cannot hold the future. Age would affect unused parts as well. Rubber hardens, lubricants separate, adhesives weaken, and batteries degrade. Radiation can damage sealed electronics, while metals and plastics slowly become less reliable. The ship would therefore need more than spares. It would need the ability to manufacture. Workshops could reshape metal, print plastic components, cut seals, wind coils, repair circuit boards, and rebuild mechanical assemblies from recovered materials. A failed housing could be melted down, purified, and formed again. Damaged wiring could become raw copper. Structural panels from abandoned sections could be cut into supports for systems still in use. This would turn maintenance into a kind of internal mining. The ship could not search a continent for ore, but it would contain metals, carbon, ceramics, glass, and polymers distributed through every wall and machine. Parts of the vessel that were no longer essential might become material reserves. A disused cabin could be dismantled to repair a water plant. Decorative panels could become shielding. An old antenna might provide rare metals for medical equipment. Yet, recycling a machine is more difficult than recycling a bottle. Modern technology depends on materials chosen for very specific properties. A bearing may require an alloy that remains strong under heat and friction. A window may use layers that block radiation while staying transparent. A computer chip depends on structures far smaller than any ordinary workshop can produce. Melting everything together would destroy the qualities that made the original components useful. The ship's industrial system would have to separate materials with great care. It would need furnaces, chemical processing, precision tools, clean rooms, and stores of elements used only in tiny amounts. Some substances would be common. Others might exist in quantities so small that losing a few kilograms could limit an entire category of repairs centuries later. Electronics would be among the hardest problems. Mechanical parts can often be measured and recreated at visible scale. Advanced processors, memory systems, and sensors require manufacturing environments that are complex even on Earth, supported by supply chains spread across many countries. A Starship might produce simpler electronics, but rebuilding its most advanced systems could demand an industrial base almost as large as the civilization that launched it. This would force the crew to decide what level of technology they truly needed to preserve. A sophisticated control system might operate efficiently, but if it failed beyond repair, a simpler replacement could be more valuable. The ship could gradually redesign itself around technologies that future generations understood and could reproduce. Performance might decline while survivability increased. Some old systems might remain in place only because no one wanted to risk replacing them. A reactor controller, navigation unit, or environmental computer could continue working long after its design as expected, patched with new software and surrounded by improvised support hardware. Engineers might understand its behavior without fully understanding its construction. They would know which warnings mattered and which sequence of restarts kept it stable. But the machine itself would become inherited technology. Over time, maintenance manuals would no longer be enough. Instructions written before launch described a system as it was built, not as it exists after 200 years of repairs. Pipes would be rerouted, components would be replaced with substitutes, software would be modified to work around damaged sensors. A person reading the original plans might see a ship that no longer existed. The true design would survive in layers of records, annotations, and practical habits. Engineers would leave messages for people they would never meet, explaining why a valve must not be opened beyond a certain point, or why a section of cable carries a load it was never intended to handle. A repair made during one emergency could become a permanent feature, and its purpose might be forgotten if the explanation was lost. Documentation would become a physical survival system. A missing note could be as dangerous as a missing part. If knowledge about a repair disappeared, the next generation might remove something that looked unnecessary, restore a system to its original configuration, and unknowingly recreate the failure that forced the change. Education would therefore be tied closely to maintenance. Children would not simply learn how machines work in theory. They would grow up inside the machines their lessons described. A class on pressure might take place beside the hull. Chemistry could be taught through water recovery. Engineering students might begin with old valves and broken pumps before they were trusted near active systems. The ship would need more trained people than daily operations seemed to require. A community that depended on one expert for a reactor, medical device, or manufacturing process would be only one accident away from losing that knowledge. Skills would have to overlap. Apprentices would begin early, and records would be written so that a capable person could recover knowledge after years of disuse. This could force the crew to keep old methods active. Certain objects might be manufactured not because they were urgently needed, but because allowing a production line to remain silent for 50 years would risk losing the ability to restart it. A workshop could become a school, a factory, and a form of cultural memory at the same time. Energy would limit how much industry the vessel could maintain. Melting metal, purifying chemicals, running clean rooms, and operating precision machinery all require power. A community facing an immediate shortage might postpone maintenance or material recovery to protect life support. The decision could be reasonable in the moment and dangerous over decades. Deferred work accumulates, and a machine that could have been repaired early may later require complete replacement. The same pattern would appear across the vessel. A small leak consumes reserve gas. A worn bearing increases power use. A misaligned pump vibrates against its housing, damaging nearby parts. Individually, these problems may seem manageable. Together, they reduce the margin that protects the ship from larger failures. The crew would have to decide not only what could be repaired, but what should be abandoned. A laboratory might be dismantled because its research was no longer essential. A habitat section could be sealed after structural damage. Historical equipment might be stripped for rare components needed elsewhere. A room where the first children were born could later become storage, and a window that once showed the shrinking sun might be removed for its layered glass. There would also be machines too complex to recreate and too important to lose. A damaged medical scanner, reactor component, or navigation instrument could become the focus of years of work. Engineers might build external supports around it, replacing everything except the part they could not reproduce. Such systems would quietly shape the society around them. If a reactor could support only a certain load, the whole community would learn to live within that limit. If the only remaining precision fabricator required rare feedstock, its use might be reserved for problems judged important enough. Maintenance would become political as well as technical, because resources given to one system could not be used elsewhere. The vessel would probably become less uniform with age. New parts would sit beside old ones. Some corridors would use advanced displays, while others relied on physical gauges because they were easier to repair. One section might be controlled by software written on board, while another operated through switches installed before launch. The ship would no longer resemble a single machine built at one moment. It would become a layered structure shaped by every generation that survived inside it. Even the hull would carry that history. Microscopic impacts, radiation, temperature changes, and stress from rotation would slowly affect the structure. External robots could patch damaged areas, replace shielding, and inspect surfaces no person could safely reach. But those robots would also age, and repairing them would require the same industrial systems they were meant to protect. Eventually, the crew would have to create tools capable of maintaining the tools that maintained the ship. A manufacturing machine cannot be treated as permanent simply because it produces replacements for everything else. Its motors, lenses, control systems, and precision surfaces also wear. The ability to reproduce ordinary parts is not enough if the equipment needed to make them cannot itself be rebuilt. This is the deeper requirement of a self-sustaining starship. It must preserve not only objects, but chains of production. It needs the tools to make parts, the tools to repair those tools, the materials to feed them, and the knowledge to operate every stage. A missing link can make an entire workshop useless, even when most of its machinery remains intact. Earth solves this problem through scale. Mines, factories, universities, transport networks, and millions of workers support one another. No single city contains every process required to rebuild modern civilization. The last Starship would have to compress a small but complete version of that network into a closed vessel while carrying its mass through interstellar space. Perfect completeness may be impossible. The ship would probably preserve some technologies while allowing others to become simpler. It might abandon devices that require rare materials and favor designs based on common metals, glass, ceramics, and reusable chemicals. Its descendants could live with tools less advanced than those available at launch, but far more repairable. This would not necessarily mean steady decline. People raised aboard the vessel would understand its systems in ways the original designers never could. They might develop materials better suited to recycling, machines built from interchangeable parts, and methods that use biological processes instead of complex industry. The ship could become more capable in some areas, even as it lost others. But every improvement would still occur under a fixed condition. There is no external source of replacement. A failed experiment consumes real material. A design mistake can damage equipment that took decades to build. Innovation would have to coexist with caution because the community could not afford unlimited attempts. As centuries passed, the distinction between the ship and its inhabitants would become less clear. The vessel would survive only through continuous human care, while the people could survive only through its machinery. Engineers, farmers, doctors, teachers, and manufacturers would form part of one extended life support system, each maintaining conditions the others required. And the more completely human survival depended on that partnership, the more important another question would become: whether the bodies born and raised inside this artificial world could remain healthy enough to keep caring for it. The adults who first entered the Starship would carry bodies shaped by Earth. Their bones would have grown under the pull of a planet. Their hearts would have learned to move blood against gravity. Their balance would have been trained by a world with a clear direction beneath their feet, and their internal clocks would have followed days created by sunlight rather than software. Even after many years in space, their biology would still carry the history of the environment in which it developed. Children born aboard the vessel would have no such history. Their bodies would begin forming inside an artificial habitat whose gravity, light, radiation, air, diet, and microbial life had all been designed rather than inherited from nature. The ship might reproduce many conditions found on Earth, but small differences that seem harmless to an adult could matter greatly during pregnancy, infancy, and adolescence, when organs and bones are still taking shape. Gravity would be one of the clearest concerns. A starship intended to support generations would probably need rotating habitats, using motion to press people toward the outer walls and create a sensation similar to weight. The floor would feel solid, objects would fall, and people could walk without floating. Yet this artificial gravity would not be exactly the same everywhere. It could be weaker near the center of rotation and stronger farther outward, while rapid movement might create sensations that do not exist on a planet. Adults could learn to live with those effects, and children raised there might adapt even more easily because their sense of balance would develop within that environment. What felt strange to the first crew could become ordinary to those who followed. The deeper question would be whether adaptation was enough. Bones respond to the forces placed upon them. Muscles grow stronger when they work against resistance. The heart and blood vessels develop according to the demands of circulation. If the artificial gravity were lower than Earth's, children might grow taller, develop lighter skeletons, or form bodies better suited to the ship than to a planet. They could be healthy in the environment they knew, while becoming less capable of living under stronger gravity later. This would complicate the mission's original purpose. A vessel traveling toward another world may be intended to land, yet generations born during the journey might not be physically prepared for that destination. If the planet had gravity close to Earth's, the people arriving there could face exhaustion, bone stress, circulation problems, and difficulty standing. A body that had spent its entire life in weaker gravity might experience a normal planetary surface as a heavy and punishing place. The ship could reduce this risk by maintaining Earth-like gravity throughout most living areas. Rotating structures large enough to do so comfortably would require enormous engineering, but the benefit could be essential. Exercise would still remain part of daily life. Muscles and bones need varied movement, impact, and resistance, not simply a constant downward force. Children would need space to run, climb, play, and fall safely, because those ordinary activities are part of how the body learns to control itself. Pregnancy would bring even greater uncertainty. Human reproduction has evolved under conditions that have remained broadly stable for millions of years. The earliest stages of development are guided by chemical signals, pressure, movement, and the structure of tissues forming at precise times. Scientists can study some effects of altered gravity using animals, cells, and short missions, but a multi-generational starship would move far beyond what could be tested completely before departure. Even with artificial gravity, the medical team would watch pregnancies closely. They would need to understand how circulation changes inside the rotating habitat, whether the developing inner ear forms normally, and how the mother's bones, muscles, and immune system respond over many months. Birth itself would have to remain safe, even if the ship were damaged, power were limited, or a medical system failed. A hospital on Earth depends on specialized medicines, sterile instruments, laboratories, imaging systems, and professionals trained for unusual emergencies. The Starship would have to preserve as much of that network as possible inside a limited volume, while accepting that some treatments could eventually become unavailable. Medical care would lean heavily on prevention, detailed family records, and the careful transfer of knowledge from one generation of doctors to the next. In a small community, every avoidable death would alter more than one family. It would change the future structure of the population. Radiation would add another layer of pressure. Earth's atmosphere and magnetic field shield life from much of the high-energy radiation moving through space. A starship between stars would be exposed to particles arriving from distant cosmic events. as well as radiation produced by its own power and propulsion systems. The hull could block part of it, but complete protection would require so much mass that the vessel might become impractical. Living areas would likely be buried behind water tanks, supplies, structural material, and specially designed shielding. Sleeping quarters, nurseries, and medical spaces would receive the strongest protection because exposure accumulates across a lifetime, and developing tissues are especially vulnerable. The danger would rarely be visible. Radiation can damage cells, raise cancer risk, affect reproductive tissue, and alter genetic material without causing an immediate crisis. Doctors could monitor exposure and treat some of its effects, but it would remain part of the background cost of living between stars. The ship's air and food would shape development in quieter ways. A carefully controlled atmosphere might contain fewer natural variations than air on Earth. Diets could be nutritionally complete, while still lacking the diversity created by thousands of plants, animals, and regional foods. Small shortages or imbalances might affect growth only after years, especially if they influenced hormones, bone formation, or the nervous system. The medical team would need to look beyond obvious disease. A generation could appear healthy while becoming slightly more vulnerable to infection, less fertile, or more dependent on a particular diet. Those changes might not become clear until the people born with them reached adulthood. By then, the system responsible could have been operating for decades. Human bodies also carry communities of bacteria and fungi that help digest food, train the immune system, and protect against harmful species. The first crew would bring only a small sample of Earth's microbial diversity aboard, and that hidden population would change over time. Some organisms would disappear, while others would spread through shared air, water, surfaces, and food systems. Cleaning could control dangerous microbes, but an environment made too sterile might weaken the diversity that helps keep people healthy. The ship would develop a microbiome of its own, useful in many places and dangerous in others. Isolation could remove some diseases because no new infections would arrive from outside. Yet it could also leave future generations poorly prepared for organisms on another world. Landing on a living planet would therefore mean entering an unseen biological environment for which their bodies had almost no experience. Even a world without native life could present danger. Dust, minerals, atmospheric chemicals, and unfamiliar gravity could challenge lungs, skin, and circulation. The people arriving there might need protective habitats for many years, perhaps permanently. The Starship could reach a habitable planet only to discover that its passengers had become a form of indoor life. Light and routine would shape health as surely as food. The ship could create regular days and nights to guide sleep, hormones, metabolism, and mood, but darkness would be produced by dimmed lamps rather than the turning of a planet. Stable schedules would matter because fatigue weakens judgment, and a vessel depending on constant human attention could not afford widespread exhaustion. The interior would also need places for play, exercise, privacy, ceremony, and contact with living plants. These would not be luxuries. Stress influences immunity, reproduction, and childhood development, so the environment would have to protect the minds of the people responsible for protecting the ship. Children would require particular care because they could not choose the world into which they were born. Their education would include the technical knowledge needed for survival, but their lives could not consist entirely of preparation for duty. A society that treated every child only as a future engineer, doctor, or farmer might preserve skills while damaging the people expected to use them. The adults would have to allow room for curiosity, disagreement, art, and identities that did not fit immediate needs. This might seem inefficient on a ship where every resource mattered, yet human flexibility often comes from activities that do not have an obvious survival value. A child fascinated by music could later understand patterns useful in engineering. Someone drawn to history might preserve lessons hidden in old failures. A healthy civilization needs more kinds of minds than any plan can assign in advance. Generational change would eventually become visible in the body itself. People might grow with different posture, muscle distribution, immune responses, or tolerance for the ship's atmosphere. Some changes would come from development, while others could arise through natural genetic variation. In a small population, chance has a stronger influence. Traits can become common not because they are better, but because the people carrying them happened to have more children. Medicine might also be used to protect the population's future. Gene therapies could remove serious inherited diseases, while stored cells and embryos from Earth could preserve genetic diversity. Such tools might be necessary, but every intervention would shape people who had no voice in the decision. The community would have to distinguish between treating disease and redesigning human beings for the environment. Even without deliberate change, adaptation could become unavoidable. After enough generations, the people aboard might remain fully human while becoming better suited to rotation, controlled diets, artificial light, and enclosed spaces. A planet judged comfortable by Earth standards could then be difficult for bodies shaped by the vessel that carried them there. Before any of those choices became real, the ship would have to maintain something more basic, a sequence of healthy generations. One successful birth would not secure the future. Children would need to survive, grow, learn, form relationships, and raise children of their own. Fertility would have to remain high enough to continue the population, but controlled enough to stay within the limits of food, space, and medical care. This would turn reproduction into both a private human experience and a shared survival concern. Every birth would carry hope, yet each one would also change the ship's future demand for air, water, food, education, and living space. Too few births could leave the vessel without enough workers or genetic diversity. Too many could place pressure on systems that could not expand quickly. And once survival depended on healthy generations being born inside the ship, the future of humanity would become a question not only of medicine, but of how many people the vessel could safely carry through time. A starship could be built with a clear capacity. Its farms would produce a certain amount of food, its water systems would recover a certain volume each day, and its living spaces would provide enough room for a planned population. Those numbers might appear stable on paper, yet a human community does not remain still. People are born, grow older, become ill, form families, change their minds, and die at times no schedule can predict. The population would move through the vessel like another living system, always shifting and never entirely under control. Too few people could be as dangerous as too many. A small crew might consume fewer resources, but it would carry less genetic diversity, fewer skills, and less ability to absorb loss. One accident could remove the only surgeon. A sudden illness could affect most of the people trained to maintain the reactor. A generation with unusually few children could leave the ship with too many older adults and not enough younger workers to replace them. A larger population would create resilience. More people means more knowledge, more possible teachers, more varied experience, and a better chance that rare talents survive from one generation to another. It also reduces the genetic influence of any single family line. But every additional person requires food, water, air, medicine, space, heat control, education, and years of care before becoming capable of supporting the community. The ship would therefore need a population large enough to remain healthy and flexible, but small enough to fit within limits that could not easily expand. There would be no empty continent beyond the walls. A crowded habitat could not relieve pressure by building outward unless new modules, shielding, and life support capacity were manufactured from material already aboard. Even if the vessel had been designed with unused space, opening it would demand energy and maintenance that might be needed elsewhere. Population planning would begin long before a crisis appeared. The crew would need to understand not only how many people were alive, but how old they were, what skills they possessed, how many children might be born, and how the age structure would change decades later. A stable total could hide an approaching problem. If most of the population belonged to one age group, the ship might face a sudden shortage of workers or caregivers when that group grew old. The timing of births would matter almost as much as the number. Children born too closely together would require schools, medical care, food, and attention at the same time. If births were spread too widely, generations might become isolated from one another, with too few people of similar age to form healthy social lives. The community would need continuity, not simply replacement. Human reproduction, however, cannot be managed like a mechanical cycle. It involves love, privacy, grief, identity, and deeply personal choices. A system that treated births only as numbers would create harm even if its calculations were correct. Yet a society that ignored the ship's limits could place everyone at risk. The tension between individual freedom and collective survival would not have a simple answer. People might be encouraged to delay or advance parenthood according to demographic need. Access to contraception, fertility treatment, and genetic counseling could help families make informed decisions. The ship might offer larger living spaces or additional support during periods when more children were needed. But even gentle incentives could feel like pressure when the entire future of humanity was used to justify them. The opposite situation would be harder. If the population approached the vessel's capacity, leaders might ask families to postpone having children. A temporary request could become a rule. A rule could become a system of permission. Once reproduction required approval, the ship would face one of the most intimate forms of authority imaginable, and every decision would carry consequences beyond the people directly involved. No policy could remove uncertainty. Some couples would be unable to have children. Others might have unexpected pregnancies. Medical complications could reduce fertility across the population. A disease, contaminant, or radiation event might not reveal its full effect for years. The ship would need room for error, because a plan that works only under perfect conditions is not a plan for survival. Stored genetic material could provide an important reserve. Sperm, eggs, embryos, and cells collected from a broad population on Earth might be preserved in protected vaults. These archives could introduce new genetic variation long after launch, reduce the risk of inherited disease, and help the community recover after demographic loss. In a biological sense, the ship might carry far more people than those who were awake inside it. The archive would still depend on machines. Samples would need stable temperatures, reliable power, shielding, and careful records. A failure in one storage unit could erase thousands of possible family lines without any visible change in the living population. Redundant vaults placed in separate sections would reduce the risk, but they would also require more equipment and maintenance. Genetic diversity is not simply a matter of avoiding close relatives. Small populations are shaped by chance. A harmless trait can become common because several people carrying it happen to have many descendants. A useful variation can disappear after one family suffers an accident. Over time, random changes may narrow the population even if every partnership is carefully planned. Medical screening could reduce some risks, while genetic therapies might correct serious inherited conditions. Yet the more the community intervened, the more it would need to decide which differences required treatment. A gene associated with illness in one environment might be harmless in another. A trait that seems unnecessary could become valuable when conditions change. Preserving diversity would mean accepting some uncertainty rather than trying to design a perfectly uniform population. This would give relationships a significance they do not carry on Earth. Two people choosing to have a child would still be making a private commitment, but their decision would also become part of the population's long future. The knowledge of that responsibility might strengthen some families and burden others. Children could grow up feeling that they had been born to fill a demographic need, rather than because they were wanted as individuals. For the society to remain healthy, it would have to resist that idea. Every person would need to be valued as more than a worker, a genetic contribution, or a consumer of resources. A population can remain numerically stable while becoming emotionally damaged, distrustful, and unable to cooperate. Survival depends on relationships that cannot be measured as easily as oxygen or calories. Death would change the calculations just as deeply as birth. A person who died young would leave behind more than grief. Their skills, experience, unfinished work, and possible children would disappear from the future. In a large civilization, such losses are absorbed across millions of lives. On the ship, one death could alter the balance of an entire generation. Even ordinary aging would need careful preparation. Older people would carry deep knowledge of the ship, but they might also require more medical care and less physically demanding work. Their experience could not simply be stored in a database. Much of it would consist of judgment, built through years of small decisions, unusual repairs, and memories of past failures. The community would need time for that knowledge to pass to younger people before illness or death removed it. A well-balanced population would include children, working adults, and elders in proportions the ship could support. This balance would shift after accidents, epidemics, or periods of low fertility. A generation might need to carry more responsibility earlier than expected. Another might spend much of its life caring for a large older population while also raising enough children to prevent decline. A model might show that more engineers were needed, but children cannot be ordered to become engineers. They can be educated, encouraged, and shown why the work matters, yet they will still have different abilities and interests. A community that forces every person into a predetermined role may fill its schedules while losing creativity, motivation, and trust. Training would have to be broad enough that critical knowledge did not depend on one individual. Doctors might learn basic engineering. Farmers could understand water treatment. Teachers could be trained in emergency medicine. This overlap would reduce efficiency in the present, but it would protect the future from sudden loss. At the same time, some tasks require years of specialization. A complex reactor, surgical system, or genetic archive cannot be maintained through general knowledge alone. The ship would need a steady sequence of apprentices, mentors, and replacements. Population planning would therefore include not only births and deaths, but the slow movement of knowledge from one generation to the next. An unexpected population decline could become difficult to reverse. If too few children were born, the community might still appear stable for years while its future workforce quietly disappeared. By the time the shortage became visible, the missing generation could not be created quickly. Babies require decades to become experienced adults, and no machine could compress that time. Rapid growth would bring a different danger. A successful period of births might fill schools and living areas while placing increasing pressure on food production. The effects would arrive slowly enough to seem manageable until the young population reached adulthood and began forming families of its own. Demographic momentum could push the ship beyond capacity even after birth rates were reduced. The vessel might respond by expanding, but expansion would never be free. New habitats require structural material, radiation shielding, air circulation, water lines, emergency access, and energy. The ship would have to decide whether to use its limited industrial capacity to create more living space or preserve the systems already keeping people alive. If expansion were impossible, The community might face choices no one at launch wanted to imagine. It could accept a smaller population, restrict births, reduce individual living space, or lower standards of comfort and nutrition. Each response would change the society, and none would feel purely technical to the people living through it. The most dangerous moment might come when different groups no longer agreed on the acceptable balance. Younger adults could resist rules written by an older generation. Families might believe their sacrifices were greater than those of others. Workers maintaining essential systems could demand more influence. People whose children were denied permission to be born would not experience that decision as an abstract calculation. At that point, the population problem would become inseparable from power. Someone would have to set limits, interpret forecasts, distribute scarce space, and decide how much freedom the vessel could risk. Even a careful and compassionate system would make choices that shaped who could form a family, which skills were preserved, and how the burdens of survival were shared. The last Starship could not avoid governing its population. Refusing to decide would still be a decision, because unchecked growth or decline would create consequences of its own. The real question would be whether those choices could be made in a way people considered legitimate, especially when there was nowhere else to live and no outside society against which the rules could be judged. And as the population learned that its future depended on decisions reaching into family, work, health, and personal freedom, the survival of humanity would begin to depend on what kind of society could hold such power without tearing itself apart. A community on Earth can survive disagreement, partly because people can leave. They can move to another city, change jobs, join another institution, or separate themselves from rules they no longer accept. A nation can fracture without taking the entire planet with it. A starship would offer no such distance. Every argument would remain inside the same hull, among people who still depended on the same air, water, food, and power. That would make politics unusually physical. A damaged relationship between two groups could affect maintenance schedules. Distrust in leadership could delay an emergency decision. A strike in a workshop might interrupt the production of spare parts. A protest near a control room could become a risk to life support systems even if no one involved intended harm. Social stability would not be separate from engineering. It would be one of the systems keeping everyone alive. The first generation might accept strong authority because it remembered the mission's original purpose. Its members may have trained together, understood the risks, and chosen to leave Earth under a clear command structure. Their laws could be based on procedures written before launch, when specialists on the ground still expected to guide the journey. But those rules would begin to lose meaning as the mission changed and the people who created them disappeared. Children born aboard the vessel would not have agreed to the journey. They would inherit its limits without choosing them. A rule that felt like necessary discipline to the founders might feel like inherited control to their descendants. The promise of arrival could no longer justify every sacrifice if the destination remained uncertain, and the memory of Earth would carry less authority with each generation. The ship would need a government capable of changing without becoming unstable. Too rigid a system might preserve order while building resentment beneath it. Too flexible a system might allow every crisis to reopen basic questions that had to be settled quickly. The community would require rules strong enough to protect essential systems and adaptable enough to remain legitimate in the eyes of people born into entirely different circumstances. Legitimacy would matter because force alone could not maintain a civilization for centuries. Security officers might protect a reactor or control a corridor, but they could not repair every machine, teach every child, or compel genuine cooperation across generations. Most of the ship's survival would depend on people choosing to perform difficult work even when no one was watching. That kind of commitment requires trust. Trust would be difficult to maintain in a closed world. Some jobs would be more dangerous. Certain families might receive larger living quarters because of medical needs. Technical workers could have access to restricted areas or information that others were not allowed to see. Leaders might need privacy during an emergency, but secrecy could easily become a habit. Even small inequalities would be visible. There would be no distant wealthy district and no hidden rural region. Everyone would move through the same limited spaces and see how others lived. If one group consistently received better food, more privacy, or safer work, resentment would not remain abstract. It would appear in classrooms, dining areas, and maintenance teams. Work would also carry a different meaning. A starship would require certain tasks whether anyone found them appealing or not. Filters must be cleaned, waste processed, crops inspected, children taught, and failing structures repaired. The community could use education, rotation, incentives, or social honor to make these roles desirable. But someone would still have to perform work that was tiring, unpleasant, or dangerous. Compulsion might appear efficient during crisis. Leaders could assign labor according to skill and need. Yet a society that treated people only as workers would damage the cooperation it depended upon. The challenge would be to make necessary work meaningful without turning every life into a duty owed to the ship. Justice would be equally complicated. On Earth, punishment often relies on separation through prison, exile, or removal from a profession. The Starship would have limited space for confinement and nowhere to send someone permanently. Every adult might be needed. A person who committed a serious crime could still be the only specialist able to repair a vital system. The community would have to think carefully about what punishment was meant to achieve. Protecting others would remain essential, but long isolation might damage both the individual and the ship. Rehabilitation, supervision, restricted access, and restorative justice could be more practical than simply locking people away. Some acts, however, would be too dangerous to treat lightly, especially violence, sabotage, or deliberate interference with life support. A murder would remove more than one life. It could erase a parent, a teacher, a rare genetic line, or a specialist whose knowledge had taken decades to develop. Sabotage could place thousands at risk. The law would reflect consequences magnified by the small size of the community. Fear of those consequences could also justify extreme control. Leaders might monitor communication, movement, and relationships in the name of safety. Surveillance would be easy to build into a vessel, where every room already contained sensors for air, heat, and maintenance. A system designed to detect leaks could also track people. The boundary between protection and intrusion would be hard to preserve. A closed habitat cannot ignore unusual behavior near a reactor or genetic archive. Yet a society in which every action is recorded may become orderly at the cost of trust, creativity, and private thought. People need spaces where they are not constantly observed, even when the world around them is small. Privacy would become a resource. Its absence would affect mental health, family life, and the ability to change. Young people would need room to form identities different from those expected by their parents. Adults would need places to argue, grieve, and rest, without becoming part of the public life of the vessel. Without privacy, every mistake could follow a person for life. Rumors would move quickly. A child might inherit a family reputation created before they were born. The community would need ways to allow forgiveness and reinvention, even when no one could disappear into a larger society. Disagreement would not be a failure by itself. A healthy society must allow people to question its direction. The danger would come when one group tried to control the systems everyone needed in order to impose its beliefs. Institutions would have to protect both debate and the life support network. Physical design could help. Critical systems might be separated from public areas and protected by several levels of access. No single person or group would control every function. Decisions affecting the whole population could require agreement across different institutions, while emergency authority would expire unless renewed. Redundancy in government could serve the same purpose as redundancy in engineering. A ship does not rely on one pump when a second can prevent disaster. A society should not rely entirely on one leader, one family, or one profession. Councils, elected representatives, courts, technical boards, and community assemblies could balance one another, though each layer would make decisions slower. Speed would matter during emergencies. A hull breach, epidemic, or reactor problem might demand action before debate was possible. The ship could grant temporary power to trained crisis teams, but it would need a clear way to return that power afterward. Emergency authority that never ends becomes a different form of government. A severe shortage would test every principle. A failed harvest, damaged factory, or decline in energy production could force the community to ration food, close living areas, delay treatments, or suspend non-essential work. These choices would not affect everyone equally. Children, pregnant people, and essential workers might receive priority. Older passengers could be asked to accept fewer resources if the next generation were at risk. Some would see this as necessary. Others would see it as the moment the society stopped valuing all lives equally. There may be no perfectly fair answer when a closed world forces choices between real harms. What would matter is whether people trusted the process, understood the evidence, and believed those making the decision were also sharing the burden. Conflict would often grow from cumulative pressure rather than one dramatic event. Crowded living spaces, long work cycles, limited choices, and inherited grief could slowly change how people treated one another. A dispute over food might actually express anger about reproduction rules. Resistance to maintenance work might be rooted in distrust of leadership. The visible issue would not always be the true one. Mental health care would therefore be part of social stability. Counselors, mediators, teachers, and community leaders could help people process isolation and loss before those pressures became dangerous. Their work would be as important as technical maintenance, even if its value was harder to measure. The ship would also need room for joy. Music, games, art, humor, friendship, and personal ambition would not be luxuries. A civilization focused only on preventing death would eventually feel like a system rather than a life. People need reasons to preserve a future they cannot yet see. Young generations would shape that future most deeply. They might question why they should preserve traditions tied to a planet they never knew. Some would demand greater freedom. Others might become more conservative than their parents, fearing that change could endanger the ship. Their arguments would alter the society far more than any plan created before launch. Over time, the political map of Earth would mean less. National identities might survive through language and family history, but the ship would create new divisions based on habitat, profession, belief, ancestry, or generation. Agricultural workers might see the vessel differently from people near the reactor. Descendants of the original crew could claim special status, while others rejected the idea that history granted authority. A stable civilization would need to stop those differences from hardening into permanent classes. Shared education, movement between professions, mixed living areas, and common service could help. So could a story about why the ship existed and what its people were trying to protect. But that story could not remain fixed forever. The founders may have described the mission as a journey to a new world. Generations later, the destination might still be distant or no longer seem viable. A society built entirely around arrival could lose purpose if arrival remained uncertain. The community would need an identity broad enough to survive changes in destination, technology, and belief. It would have to understand itself not merely as passengers waiting for a future, but as a human world already in existence. That shift could allow people to build meaningful lives inside the ship, rather than treating every year as a temporary delay. Yet becoming a world would raise another question. A world is more than rules, population, and functioning machines. It is also memory. It knows where it came from, why its customs exist, and what earlier generations discovered at great cost. Without that continuity, the ship might remain inhabited, while the civilization it carried slowly became unrecognizable. And so, the society's ability to govern itself would eventually depend on whether it could preserve enough of Earth's knowledge, stories, and experience to remember what humanity had once been. At the beginning, memory would still live inside people. The oldest passengers would remember the weight of rain on clothing, the sound of traffic beyond an open window, the smell of soil after a storm, and the strange freedom of walking in a direction without meeting a wall. They would remember nations, cities, coastlines, animals, and seasons not as recordings, but as parts of ordinary life. For those born aboard the ship, these memories would arrive through someone else's voice. A child might hear about forests from a grandparent who had crossed one on foot. Another might learn about oceans from a person who had once stood beside one. The stories would be detailed, emotional, and personal. Yet, they would describe a world the child could never verify through experience. That difference would grow with each generation. The first people born in deep space might still know passengers who had lived on Earth. Their children might know only those who had heard Earth described directly. Later generations would inherit memories that had passed through many minds, changing slightly each time. A detail could be forgotten, simplified, exaggerated, or given new meaning by people whose lives were completely different from those of the storyteller. The ship would almost certainly contain vast archives. Images of cities, recordings of languages, films, books, maps, scientific papers, medical knowledge, engineering plans, music, art, and historical records could all be stored in a volume far smaller than the physical world they described. A digital library might contain more knowledge than any single person could absorb in a lifetime. Yet storing information is not the same as preserving it. Every archive depends on hardware, software, power, and interpretation. Data written in one format may become difficult to read after the machines designed for it have disappeared. A storage system can remain physically intact while the knowledge required to access it is lost. Files may survive, but without working devices, compatible programs, or people who understand the language, they become silent objects. The ship would need to copy its archives again and again. Old storage would be replaced before it failed. Important records would exist in several locations so that fire, radiation, or mechanical damage could not erase everything at once. Some knowledge would be printed or engraved onto durable materials that could be read without electricity. The most essential information might be preserved in several forms, from simple diagrams to detailed technical records. Practical knowledge would be especially fragile. A manual can explain how a machine works, but it cannot fully replace experience. An engineer who has repaired the same pump for 30 years knows sounds, vibrations, and small irregularities that may never appear in official instructions. A surgeon understands more than the steps of an operation. A farmer sees patterns in leaves that a textbook may describe but cannot make familiar. The community would need apprenticeships as much as libraries. Young people would learn beside older workers, watching how they respond when reality differs from the manual. This knowledge moves through demonstration, correction, habit, and trust. It is slow to build and easy to lose. A sudden death could remove years of unwritten understanding. If several specialists from one field were lost together, the ship might retain all of their records while losing the ability to apply them well. The community would try to prevent this by spreading knowledge among several people, recording unusual repairs, and avoiding systems that only one expert could understand. Education would become part of life support. Children would need to learn reading, mathematics, science, history, medicine, engineering, agriculture, and the social knowledge required to live in a closed world. They would also need art, language, play, and enough freedom to develop ideas the founders had never imagined. A school designed only to reproduce existing skills might preserve the ship for a time, while slowly weakening its ability to adapt. A purely practical answer would be dangerous. The ship needs technicians, doctors, and farmers. But it also needs people who understand why certain choices were made, how power has failed before, and what human beings can become under pressure. History could help the community recognize patterns that engineering alone cannot solve. Art would carry another kind of memory. A song can preserve emotion long after its original context is forgotten. A film can show movement, landscape, and human expression more directly than a technical description. Paintings, novels, and stories would help later generations understand that Earth was not only a system of air and water, but a place where billions of different lives once unfolded. Not everything could be preserved equally. The archive might begin with millions of books and recordings, but attention would remain limited. Some works would be taught repeatedly, while others were rarely opened. Over centuries, a small selection could become the cultural center of the ship, simply because teachers found them useful, moving, or easy to understand. This process could make the surviving picture of Earth narrower than Earth had ever been. Whole cultures might be represented by a few recordings. Smaller languages could disappear if too few speakers remained. Regional traditions might survive only through recipes, songs, or family stories whose meaning gradually changed. Families might preserve their own traditions privately, passing names, stories, and rituals from one generation to another. Public institutions could maintain broader archives, while schools taught a common history. Over time, the difference between family memory and official history could grow. A community might celebrate the mission as a heroic rescue, while some families remembered it as an abandonment, an escape reserved for the chosen, or the result of decisions that had failed, everyone left behind. The day Earth went silent would become one of the most contested memories. Those who experienced it might remember confusion rather than certainty. Later generations could turn that uncertainty into a clear story because clear stories are easier to teach. They might say Earth was destroyed, even if no proof had ever arrived. Others might believe humanity still survived there and accuse the ship's leaders of giving up too soon. Scientific knowledge would need similar care. Many facts recorded at launch could become outdated as the ship collected new observations and developed new methods. The community could not preserve Earth's science as a fixed set of answers. It would have to preserve the process of testing, measuring, revising, and admitting uncertainty. This might be one of the most important inheritances the ship carried. A database can store conclusions, but only a scientific culture can correct them. Future generations would need the confidence to question the founders when evidence demanded it, even while depending on the systems the founders built. The same would be true of law and morality. Earth's history contains examples of cooperation, cruelty, freedom, oppression, discovery, and destruction. The ship could preserve these records, but it could not simply copy one society and expect it to function forever. Its people would have to study the past without becoming trapped inside it. Memory would therefore serve two opposite purposes. It would tell the community who it was, while reminding it that change is possible. If the ship preserved only tradition, it might become rigid. If it preserved only technical knowledge, it might survive physically while losing much of the human world it was meant to carry. There would also be limits to how much grief a civilization could hold. Children could not be raised only on stories of extinction and loss. Earth's destruction, if that was what had happened, would be part of their history, but not the whole meaning of their lives. They would need stories that allowed them to see the ship as a beginning, rather than merely the final fragment of a dead world. This balance would change with time. Early generations might feel a duty to reproduce Earth as faithfully as possible. Later generations could resent being told that their home was only a poor substitute. They might create new art, customs, names, and celebrations rooted in the vessel itself. The sound of pumps, the cycle of artificial day, the opening of a harvest room, or the sight of a distant star could become part of their cultural identity. Children might draw the ship's rotating habitats the way Earth children once drew houses and trees. A maintenance corridor could become the setting of legends. An old observation window might become a place where generations marked important moments. This new culture would not necessarily mean Earth had been forgotten. It could be evidence that humanity was still alive enough to create rather than merely copy. The challenge would be to let the future grow without cutting it away from the past. The line between those choices would never remain fixed. During abundance, archives and museums could grow. During crisis, resources might be redirected. A damaged habitat could force the community to choose between preserving cultural objects and creating more living space. Every emergency would test whether memory was seen as essential or optional. The archives would also contain knowledge of worlds beyond Earth. Astronomical surveys, planetary maps, and records of distant stars would guide the vessel toward possible destinations. Over time, the ship's own observations would become more important than the data loaded at launch. It would measure new planets, watch target stars change, and revise old expectations. The same institutions that preserved Earth's past would therefore help decide humanity's future. Historians, scientists, engineers, and navigators would all depend on records maintained across generations. A missing dataset or misunderstood observation could affect the choice of an entire world. Eventually, the question of where the ship came from would begin to merge with the question of where it was going. Earth would remain the reference point for what people needed from a planet. Suitable gravity, liquid water, manageable radiation, useful chemistry, and an environment where human life could continue without constant mechanical support. But memory could also make the crew see what it wanted to see. A distant planet with blue light and a thin atmosphere might be called another Earth long before enough was known. Generations raised on stories of oceans and open skies could become willing to accept risks simply for the chance to experience them. The longing for a real world would grow stronger as Earth became more distant in time. Yet the archives would contain a warning as clear as any engineering manual. A planet seen from far away can appear promising, while hiding conditions no human body could survive. And once the last starship had preserved everything it could about the world behind it, that memory would begin guiding the search for a new world that might never truly match the one humanity had lost. From a great distance, a planet can appear simple. It may pass in front of its star and remove a small amount of light. Its gravity may pull the star slightly from side to side. A faint spectrum can suggest water vapor, carbon dioxide, oxygen, methane, or clouds. From these signals, observers can estimate size, temperature, orbit, and perhaps the broad character of an atmosphere. But a world measured across light years is still mostly hidden. The target chosen before launch would have been selected from incomplete evidence. It might lie at a promising distance from its star, neither obviously frozen nor violently hot. Its mass could suggest a rocky surface, and its atmosphere might contain gases associated with a stable climate. Yet none of this would guarantee open oceans, breathable air, safe soil, or a surface on which human beings could live. Even the phrase habitable planet can create a misleading picture. In astronomy, habitability often means that liquid water could exist under some conditions. It does not mean that people could step outside without protection. A planet may have water beneath kilometers of ice, in clouds of corrosive chemistry, or in temporary pools beneath an atmosphere too thin to breathe. It may be suitable for simple organisms and lethal to every unprotected human body. The Starship would approach its destination carrying data that had aged throughout the journey. If the voyage lasted a century, the planet observed at departure would already belong to the past. Its star could have become more active. A changing atmosphere might have warmed or cooled the surface. Large impacts, volcanic events, or slow climate shifts could alter conditions while the ship was still between stars. There would be little room for disappointment. A robotic mission can pass a hostile world, collect information, and continue. The last Starship would be carrying people, farms, archives, and machinery that had already survived for generations. Its destination would not merely be a scientific target. It would represent the hope that the ship could eventually stop being the only place where humanity was alive. As the target star grew brighter, the crew would begin seeing details that had been impossible from Earth. Telescopes aboard the vessel could separate the planet's light from the glare of its star. They might map cloud patterns, measure seasons, and search for changes in atmospheric gases. Small probes could travel ahead, sending back close observations while the main ship remained at a safer distance. Those probes would be essential because arrival itself could not be reversed easily. A starship moving at even a small fraction of the speed of light carries enormous momentum. Reaching the correct star system is not the same as stopping inside it. The vessel would need to begin slowing long before the destination looked close, using fuel, magnetic systems, light sails, or some other method capable of reducing a velocity built over decades. A mistake in braking could send the ship through the system and back into interstellar space. Slowing too early could extend the journey by years and consume reserves the population needed. Slowing too late could leave no second attempt. The destination would approach gradually in the sky, while the true decision point arrived far earlier, hidden inside calculations of speed and distance. The ship might carry several possible targets within the same system. A planet that seemed ideal before launch could prove unsuitable, while a moon, asteroid, or colder neighboring world offered materials and shelter. The crew would compare choices that were all imperfect. One world might have better gravity, but a toxic atmosphere. Another could contain water, but receive dangerous radiation. A third might be easier to reach, yet offer no surface environment at all. Gravity would be among the first permanent limits. A planet much more massive than Earth could place constant strain on hearts, bones, joints, and pregnancies. People raised under the ship's artificial gravity might not adapt well to a stronger pull. A smaller world could be easier to land on, but its weak gravity might create long-term health problems and allow its atmosphere to escape more easily. The atmosphere would create another set of uncertainties. Oxygen alone would not make air safe. Pressure, nitrogen, carbon dioxide, toxic gases, dust, microbes, and reactive chemicals would all matter. A world with abundant oxygen might be biologically active in ways that threatened Earth life. It might also be chemically unstable, prone to intense fires, or filled with particles that damaged lungs. The star would shape every condition. A small red star can shine steadily for an extremely long time, yet many such stars produce strong flares and streams of charged particles. A planet close enough to remain warm could be exposed to repeated bursts of radiation. Its atmosphere might survive, but life on the surface could require deep shielding. Water would carry its own dangers. An ocean planet might contain almost no dry land. A dry world could hide water underground, but extracting it might require energy and machinery the ship could not spare. Water rich in unfamiliar salts or toxic compounds would need treatment. Ice could provide a valuable resource, yet remain locked beneath surfaces too cold or unstable for large settlements. If the planet already contained life, the situation would become more complicated rather than easier. Living organisms would show that the environment could support biology, but not necessarily human biology. Alien microbes might be harmless because they could not interact with Earth cells, or dangerous in ways no one could predict. Their chemistry might produce toxins, attack crops, or disrupt the closed ecosystems the ship had spent generations preserving. A lifeless planet might appear simpler, but creating a home there would be a vast task. The ship could build sealed habitats, mine local material, and gradually expand. It might extract water, metals, and gases, so that survival no longer depended entirely on the vessel's original stores. Even a hostile world could become useful if it supplied the raw materials needed to repair the ship and create new structures. That may be the first realistic form of arrival. Humanity would not step onto a second Earth. It would establish workshops beneath rock, farms inside pressure chambers, and living areas protected from radiation. The planet would support the settlement through resources rather than through a naturally comfortable environment. Changing the entire world would be far more difficult. Warming a cold planet, thickening an atmosphere, creating stable soil, and building an oxygen-rich biosphere could take centuries or much longer. The required materials and energy might exceed anything the remaining population could produce. Some changes could trigger consequences that were hard to reverse. The ship's population would have to decide how long it was willing to wait. Some people might want to land as soon as a protected settlement could be built. Others would prefer to remain aboard until the surface had been studied for decades. Families born during the final approach might see the planet as their promised home, while those responsible for life support understood how quickly an unknown environment could destroy the last human community. There could also be disagreement over whether to stop at all. If the destination proved poor, but another candidate lay several light years farther away, the crew might still have a choice. Continuing would preserve the possibility of finding something better, but it would place more years of strain on a ship already old. Stopping would offer resources and stability, yet could trap humanity beside a world that never became truly habitable. Fuel would make the decision permanent. Changing course or accelerating toward another star might use reserves needed for braking, power, or emergencies. The vessel could not search the galaxy freely. Every additional target would have a cost measured in time, machinery, and human lives. The archives of Earth would influence these choices. Records of blue oceans, forests, rain, and open landscapes could set an impossible standard. A planet capable of supporting a settlement might be rejected because it did not resemble the world humanity remembered. The search for home could become a search for an exact replacement that nature was unlikely to provide. Earth was not merely a rocky planet at a useful distance from a star. It was the result of billions of years of geology, climate, chemistry, and life interacting in one particular history. Its atmosphere was shaped by organisms. Its soil contained complex ecosystems. Its oceans regulated temperature, while its moon, rotation, continents, and interior all influenced the world people inherited. This does not mean that settlement would be impossible. Human beings have always adapted environments to their needs, and a starship capable of crossing interstellar space would carry extraordinary knowledge. The crew could build underground, use local materials, create artificial ecosystems, and expand slowly. But this would not be a return to natural safety. It would be the construction of another machine-supported world, spread across a planet rather than contained inside one vessel. In time, the ship and the planet could become parts of the same civilization. Children might be born who considered the surface home, while older generations preferred the controlled environment of the vessel. New divisions could form between those who lived under a sky and those who remained in orbit. Arrival would not end the human story inside the ship. It would change its shape. The real measure of a new home would not be whether people could stand on its surface for a photograph. It would be whether children could be born there, grow healthy, learn, create families, and maintain the systems needed by generations after them. A world becomes home only when survival no longer depends on a temporary reserve brought from somewhere else. The crew might discover that no destination completely meets this standard. One world could support sealed cities. Another might offer resources but no safe surface. A third could be biologically rich, yet too dangerous to enter. The search would not necessarily end with a perfect answer, only with the least dangerous future available. That realization would return attention to the vessel itself. For generations, the ship may have been treated as a bridge between worlds, valuable only because it carried humanity towards something better. But if every reachable planet still required walls, machinery, recycling, and careful control, then the difference between the journey and the destination would become less clear. The ship might already contain the most stable human environment available. It had protected births, harvests, knowledge, and society across distances no planet-bound civilization had crossed. Its limitations were serious, but they were known. A new world would offer materials and space, while introducing dangers that could not be fully predicted. This future would be less simple than the dream that launched the mission. There might be no moment when the doors opened and the journey was declared complete. The last starship could slowly become the first structure of a new civilization, its oldest systems still running, while newer habitats spread through the system around it. And yet, the central limit would remain. Whether humanity lived inside the vessel, beneath alien soil, or across many habitats, every generation would still depend on the next one, understanding how to continue. A planet could provide more resources and room, but it could not guarantee cooperation, knowledge, health, or purpose. The search for a new world would therefore reveal something larger than the conditions of any single planet. Humanity's survival had never depended only on reaching the right place. It depended on carrying a living civilization across time without allowing the chain between generations to break. And when every possible destination carried its own uncertainty, the last starship would have to face a deeper truth. Keeping humanity alive might no longer depend on finding another Earth at all. For much of the journey, survival would seem connected to arrival. The ship would be endured because it was carrying people towards somewhere else. Every repair, restriction, and sacrifice would be justified by the belief that one day the walls would open, the engines would fall silent, and human life would begin again beneath a real sky. But after enough generations, that idea would become less certain. The destination might remain too hostile. The planet might offer resources without comfort, shelter without freedom, or land that still required sealed habitats and artificial air. Even if humanity reached another star, the people who arrived could discover that the most reliable world they possessed was still the vessel that had carried them there. This would not make the journey meaningless. It would change what the journey had been. The last starship would no longer be only a bridge between a lost planet and a future one. It would be a civilization in its own right, built inside a machine, but shaped by births, memories, laws, grief, work, and hope. Its survival would depend on the same things that have always held human societies together, though every weakness would be amplified by the fact that there was nowhere else to go. The ship's lifetime could not be measured by the durability of its hull alone. A pressure vessel might remain intact, while the knowledge needed to repair it disappeared. A reactor could continue producing power while the society around it lost trust. Crops might still grow, while the population became too small, too divided, or too unhealthy to maintain them. No single failure would define the true limit. The ship would survive only while many fragile systems remained connected. Air had to circulate, water had to return, food had to grow, machines had to be repaired, children had to be born healthy, skills had to be taught, rules had to be accepted. People had to believe that the future was worth the work required to reach it. That chain could remain strong for an extraordinary length of time. With sufficient shielding, energy, manufacturing, and biological control, a carefully designed vessel might support human life for centuries. If it carried large reserves, adaptable machines, genetic archives, and a population broad enough to recover from loss, it might last much longer. Over time, parts of the original structure could be replaced until almost nothing remained from launch except the design, the records, and the name. The ship would become something like a living organism. Cells in a body are replaced, yet the person remains. In the same way, decks could be rebuilt, pipes rerouted, habitats expanded, and old systems removed without ending the continuity of the civilization aboard. The vessel might survive not by resisting change, but by changing carefully enough that each generation still understood what had been inherited. At that point, the phrase "last Starship" would become inaccurate. It may have been the last vessel launched from Earth, but it could become the first source of ships built elsewhere. If the community preserved enough knowledge and industrial ability, it might eventually create new habitats, send out small expeditions, and spread human life across a distant system. The survival of humanity would then no longer rest inside one hull. It would be divided among several places, making the failure of any single habitat less final. That separation could be the moment when the species stopped living, one accident away from extinction. Yet reaching that point would require the original ship to survive its most dangerous period, the long interval when it remained alone. During those years, there would be no second colony, no independent reserve, and no outside population to continue if something went wrong. Every birth and every repair would matter, because the entire human future remained concentrated in one moving world. The ship could contain thousands of people and still be small when measured against the scale of what it was carrying. Humanity is more than a population large enough to reproduce. It includes languages, memories, scientific methods, artistic traditions, relationships, and the ability to create new ideas. A vessel could preserve human bodies while losing much of this complexity. It could remain technically alive while becoming culturally narrow, fearful, and incapable of adapting. The opposite risk would also exist. A society could preserve art, freedom, and knowledge while allowing essential systems to decline. There is no useful culture without living people, just as there is no meaningful survival if life is reduced to permanent obedience and maintenance. The most successful community would have to protect both. It would need engineers who understood that comfort, education, and beauty were part of resilience. It would need artists and teachers who understood that air filters and nutrient cycles were not background details, but the conditions that allowed every story to continue. It would need leaders willing to make difficult decisions without turning necessity into permanent control. No design could guarantee this balance. The ship could begin with ideal institutions and still change under pressure. It could carry complete archives and still misunderstand them. It could teach every child the failures of Earth and still repeat some of them in a new form. The future would remain uncertain because people would remain human. They would disagree, become tired, act selfishly, fall in love, create loyalties, challenge rules, and make decisions whose consequences could not be known in advance. These qualities would sometimes threaten the vessel. They would also be the source of invention, compassion, and the willingness to imagine a life beyond the one inherited. A perfectly controlled population might preserve routines, but it could lose the creativity needed when those routines stopped working. A completely unrestricted society might be energetic and free, but unable to protect shared resources. The ship would survive somewhere between those extremes, adjusting again and again as conditions changed. This is why the answer to how long the last Starship could keep humanity alive cannot be reduced to one number. A reactor might operate for a century, a hull could be repaired for several. Genetic models might suggest a population can remain healthy for many generations. But none of those limits acts alone. The true lifetime of the vessel would emerge from the interaction between technology, biology, knowledge, and society. A small technical problem could become a social crisis. A political conflict could delay repairs. A period of poor education could create engineering failures decades later. A damaged farm could affect health, population, and trust. Every system would reach into the others. The ship might endure a major accident and recover because the community responded well. It might fail during a minor shortage because confidence had already collapsed. Survival would depend less on avoiding every crisis than on preserving the ability to learn from one. There would be years when the vessel felt stable enough that extinction seemed remote. Children would grow up believing the systems around them were simply part of nature. The sound of ventilation would be as ordinary as wind once was. Artificial mornings would arrive on schedule, crops would grow, and people would plan futures without thinking constantly about the darkness beyond the hull. That normality would be an achievement, not an illusion. A world becomes livable when its people are able to think about more than survival. The ship would have succeeded when children could study music, form friendships, argue about ideas, and imagine careers without every moment being defined by emergency. Still, the machinery beneath that ordinary life would never stop requiring care. The community could forget the fear of the early journey, but it could not forget the systems that protected it. One generation's comfort would depend on another generation teaching the reasons behind every routine. Earth would remain important, but its meaning would change. It would be the origin of human life, not necessarily the place to which humanity expected to return. The ship's population could honor it without allowing grief to define every future choice. Eventually, no living person would feel that they had personally lost Earth. They would feel connected to it through ancestry, culture, and biology. Much as people on Earth once felt connected to places their families had left generations earlier. The sorrow would become quieter, while the life around them became more real. This would not mean forgetting. It would mean that humanity had continued long enough for memory to stop being only pain. The final measure of the last Starship would therefore not be the number of years before its original systems failed. It would be whether the vessel could create generations capable of rebuilding what failed, changing what no longer worked, and preserving enough continuity that the people of the future still recognize themselves as part of the same human story. If the ship could do that, its life might not have a clear end. It could be repaired, divided, expanded, and rebuilt. It might become a settlement, then a network of settlements, then the beginning of a civilization around another star. The original vessel could eventually be retired, dismantled, or preserved as a monument, while the humanity it carried continued elsewhere. In that sense, the Starship would not need to survive forever. It would only need to survive long enough to make itself unnecessary. The difficult part would be reaching that future without knowing whether it was possible. Every generation would work with incomplete information. The first would not know whether the ship could support grandchildren. Later generations would not know whether the destination would be safe. Those who arrived might not know whether the new settlement could survive without the vessel. No generation would receive certainty before being asked to continue. That may be the quietest and most human part of the entire journey. People would preserve systems whose final success they would never see. They would teach children who would make decisions they could not control. They would repair a vessel for descendants who might one day leave it behind. The last Starship would keep humanity alive not through one perfect machine, one heroic crew, or one flawless plan. It would do so through a long sequence of ordinary acts performed by people who understood that someone would have to live after them. A filter changed on time, a child taught patiently, A difficult truth recorded honestly. A crop protected from disease. A law revised before it became unjust. A damaged component rebuilt instead of abandoned. None of these acts would look large enough to save a species, yet together they would form the only path by which the species could continue. And perhaps that is the final answer. The last Starship could keep humanity alive for as long as its people remained capable of renewing not only the vessel, but the civilization inside it. Its machines would matter, its resources would matter, and its destination would matter. But none of them would be enough without generations willing to inherit a fragile world and leave it stronger than they found it. The ship might cross the darkness for centuries. It might settle a distant planet, remain in orbit, or build habitats from the remains of asteroids. It might slowly lose every original part and still continue under the same name. What survived would not be the machine itself. What survived would be the chain of human lives carried through it. Thank you for watching this calm journey into the future of humanity aboard the last Starship. If you enjoyed this documentary, subscribe for more quiet space stories like this. Leave a like if you want more deep journeys into the mysteries of the universe, and tell me which part of human civilization you would choose to protect above everything else. Tonight, you are watching the Just About Space channel, talking about how long could the last Starship keep humanity alive. Sleep well and keep looking up. Good night.